Hi, I'm Tiffany,
And I'm Brad.
and this is the YSP Teaching Kit demo for surface tension.
There are a lot of different materials that exhibit the property of surface tension, but in this kit we're going to focus on water because that's such an important material in our daily lives. Now, surface tension is the property that makes water bead up and form bubbles and form raindrops. And so we're going to be visualizing that shape that the water makes in these demos that we're going to perform today.
And surface tension is an abstract concept, and that's important to remember when you're talking to your students, but we are going to show you some experiments today in ways that you can really visualize the strong property of surface tension, particularly in the context of water. So your students will do some experiments where they can visualize how water forms a bead-like structure. This dome-like shape that we can see with water, for example, when you pour it in a cup or when you drop a drop of water on a surface, is due to cohesive forces between water molecules. And these cohesive forces can form because waters are made up of negative and positive charges that can interact very strongly with each other.
Now, the reason why water is such a good material for demonstrating surface tension is because water is attracted to other molecules of water so strongly, and because it's not attracted to the air that's above it. Now, the water tries to minimize the area in which it must interact with the air, so it wants to form the smallest surface area, which in this case would be a circle or a bead shape, between the fluid and the gas interface. So one way that we can reduce the surface tension of water is by introducing another chemical called a surfactant. A common example of a surfactant is soap or a detergent. Now, surfactants are molecules that have two parts, a hydrophilic or water-loving part, and a hydrophobic or water-hating part. The reason why adding a surfactant lowers the surface tension of the water is because the water molecules can now interact with the water-loving parts of the surfactant. And the water-hating parts of the surfactant can interact with the gas above. So now the water doesn't only have to interact with other water molecules, and it doesn't need to hide from the air above, because it can interact with the surfactant molecules. So now we have a flat surface where we used to have this curve.
So within this kit, we're going to be showing you the protocols for 5 demos to show surface tension. And I just want to briefly emphasize the main point of each of these demos to you. In the first 2 demos, we will be focusing on visualizing that bead-like shape of water. In the first demo, dropping water on a penny, you can see that bead-like shape when you drop the water. Then you can also see how that's disrupted when a surfactant is added. In the second experiment, where you have a cup full of water where you're adding pennies, this is a more dramatic visualization of that beading up shape that we saw in the first experiment, but you're going to be surprised by how many pennies can be put into the water, displacing it, but the surface tension is so strong that it just keeps beating and beating up. In the third experiment, we're really going to emphasize how strong surface tension is by showing that a paperclip can actually be floated on top of water.
In the fourth demo, we will be using pepper to demonstrate how strong an effect a surfactant can have on water. The fifth demo is actually a teacher demo because it will involve an open flame. And this demo is going to demonstrate that the surface tension allows a soapy bubble to absorb enough force to blow out a candle.
Hi, I'm Erica, and I'm going to be demonstrating the first experiment, which is surface tension on the surface of a penny. For this experiment, you will need water, several paper towels, and a clean penny that you've cleaned off, rinsed, and dried, a cup for water and soap that's separate, and then 2 eye drops, 1 for each container. First, pour some water into a cup for each student. Have the students load their eyedropper with some water, and then place 1 drop on the penny. Based on this surface, on the shape they see here, you can ask your students to guess how many drops will fit on the surface of the penny. Have them count as they add more drops of water to the surface of the penny. When the water spills over onto the paper towel, they should stop counting. Then rinse off the penny and grab a new paper towel. And this time, add some soap to the container with water. You'll need to add about half to a third of the volume of soap or of water that you have in the container so that there will be enough to see a strong effect. After you add the soap, make sure to stir it around very thoroughly so that the soap is mixed in with the water. Otherwise, they run the risk of pulling up only soap instead of soap water. Then have them repeat what they did last time, pulling soapy water up into the eyedropper, and then guessing how many drops will accumulate on the top of the penny now that they've added soap, whether it will be more or fewer drops. Add them slowly, and then once again, observe when the water runs off the surface of the penny. It should be fewer drops because the surfactant interrupts the surface tension. Some things you may want to go over with your students are why there are fewer drops accumulating on top of the penny after you add soap to the water instead of just plain water. It may also be a good exercise for you to collect the number of drops with or without soap from each group in the class, and then write them on the board, average them out, and see whether there are any reasons why some groups may have experienced more or less, such as they added them at different speeds, they added more soap to their water, etc. You can also ask them to observe the shape of the water on top of the penny. Without soap, you should see a higher amount of surface tension and a greater roundness to the bubble, a more curved shape. And with soap, it should be a flatter, wider shape.
In this next experiment, you will need your cup with water and some more water to add to the cup, as well as many pennies. First, you will add water to fill the cup to the brim so that you have about a level surface at the top. Then take 1 penny and drop it very gently into the water. Then have the students guess how many pennies they can add to the water before the water spills over from the top. Then they proceed to add pennies one by one, very gently. They should notice that at the surface, the water will form that bead shape as we've discussed earlier. Still adding pennies. If you drop the pennies from an angle like this right at the edge, that will help you prevent from spilling over just from a splash like that. A few pointers that might help this experiment go more smoothly are to make sure that you add enough water at the beginning, make sure you get it all the way up to the top, or else it's going to take a very long time to get the water to spill over. Also, if the students see water drip out before you see this nice shape, the dome shape at the top of the water, then that might mean that they aren't dropping the pennies gently enough and they're just getting a splash from the penny. So remind them to add the pennies very gently.
In this third experiment, the paperclip experiment, your students will see how the force of surface tension can oppose the force of gravity. As you recall, surface tension involves the attraction of water molecules to each other. This force is called cohesion. This cohesive force is strong enough that it can resist the force of gravity on an object that's sitting on top of the water. This includes things like water bugs or a paper towel if you float it on top. You will need water, a cup that has not had soap in it before, 2 paper clips, and a piece of paper towel that's torn to about the size of the paper clip. The paper clip will need to rest on top of it, so you need to make sure that it's about the same size. You will also need soap. Fill the cup with water, and then have your students drop one of the paper clips into the water, wide side down. As you can see, the paper clip drops rapidly to the bottom of the cup. This is because the paper clip is denser than the water, and you can have your students determine this. Next, float a piece of paper towel on top of the water, and then add a second paper clip resting on the top of the paper towel. As the paper towel becomes wet, it will sink to the bottom of the cup. Okay. So don't become frustrated if this doesn't work on the first time. Sometimes the paper towel will drop, taking the paper clip with it, and this is just because they become caught together. Alternatively, they may remain stuck on the top of the water for a very long time. If this happens, you can gently poke at the water with one of the eyedroppers, or at the paper towel with one of the eyedroppers, forcing the paper towel to sink without touching the paper clip. And if you do it gently, you can sometimes leave the paper clip suspended on the surface of the water. For the final step of the experiment, add 1 drop of soap to the water. Because soap disrupts the surface tension in the water, you should see the paper clip rapidly drop down to the bottom. It may take a little while as the soap distributes throughout the water, reaching the surface. If it doesn't, you can add more soap. Be sure not to hit the paper clip with the soap. Make sure when you're doing this experiment that you do several things. The piece of paper towel should be about the same size as the paper clip, not much more. Otherwise, it'll stay on the surface of the water for too long. Make sure the paper clips are dry, otherwise they'll sink really quickly. Make sure that the paper clips are these small paper clips and not a larger one, otherwise they will sink immediately and the paper towel won't hold them up.
This next experiment, you will need a large pan, water to fill the pan, some soap, and also some pepper in a shaker. The first thing you're going to do is to pour water into the pan. So that you have a good coating all the way across. Next, you want to shake pepper so that you have it floating all over the water. And you want to make sure that you add enough so that you can see which areas of the water have the pepper on it. Now the pepper is being supported by the surface tension of the water. Next, you're going to add soap to the center of the water, and you should see the pepper move away from the soap. Now when we added the soap, that disrupted the attractive forces between the water molecules and reduced the surface tension in the middle of the pan. And that's why the pepper moved away to areas where the surface tension had not been as effective.
This final experiment is a teacher demonstration because it involves fire. What you're doing here is demonstrating the power of surface tension with a detergent, in this case shampoo. Using the tray you had before, put some detergent in the bottom of the tray and stick the funnel down into it. Slowly bring the funnel up, forming a sheet of the detergent across the surface of the funnel. In this experiment, you will be using the air held within the funnel to blow out a lit candle. As you can see, the extra air stored within the bubble because of the surface tension blows out the candle with the force of the air moving past it.
So we hope that you find this teaching kit to be a valuable resource and a helpful tool. Please fill out the survey and send it back to us with your feedback on how we can improve the procedures and the protocols and also this video so we can make them better in the future.